All right, we made it to the last video of Chapter 8. So this is 8.8, Improper Integrals, the second day. We really have just one example here, and then it's getting into review, and I'll go over some of the questions from the homework, day 90. All right, so if we have this improper integral from negative infinity to infinity of dx over 1 plus x squared, well, what we should recognize is this is eventually dealing with the arctangent, okay? So we got to think about that aspect, and what we can do is we can break it up, all right? And I'm just going to say negative infinity to 0, and then 0 to infinity. And we can do this because it's symmetric, okay? So that's kind of like our halfway point. Whatever happens over here is going to be the same as whatever happens over here. All right, so with that said, because we've got this infinite limit, right, this we need to then change. I'm just going to focus on this guy here. So I'm going to rewrite it, and remember, whatever happens here, it's happening here as well. So this is the limit as b approaches infinity of the integral from 0 to b of that dx over 1 plus x squared, which we can integrate that. That's just arctangent of x. All right, and evaluating that, we get arctangent of b minus arctangent of 0. So now we can go ahead and take the limit. So as b goes to infinity, arctangent of infinity is pi over 2. Arctangent of 0 is 0. That's kind of where I get this graph from over here. All right, so if this is our tangent function, you know, we can think, oh, at pi over 2, we're at pi over 2, 0, and 0, 0, those points. So then arctangent, 0 goes to pi over 2, and then 0, 0 here. All right, so that's just kind of reminding us of that information. So now as we go ahead and evaluate, we get this portion of our integral to be pi over 2. But remember, since it's symmetric, whatever this side is, this side is as well. So we really have this whole side equaling pi over 2 as well. So the whole integral is really equal to pi, just adding those two pieces together, again, since it's symmetric. So something to think about. All right? Okay, so now let's just go through some of those review questions on the bottom. Now, I'm going to let you kind of look through those before we go through them together. I want to see if you can answer those questions. When can L'Hopital's rule be applied? What are the other indeterminate forms? How is each one handled? And then which trig functions involve 0 or infinity? And then see if you can draw a sketch. And then we'll talk about the two types of improper integrals. So give yourself, you know, a little bit of time, pause it, see if you can answer those questions, then we'll come back and make sure you've got it all. Okay, so hopefully you did all right. When can L'Hopital's rule be applied? When we have 0 over 0 or any form of infinity over infinity. What are the other indeterminate forms? Well, our other indeterminate forms are 0 times infinity, so that's where we reciprocate. 1 to infinity or 0 to the infinity, that's when we take the ln of both sides. And then infinity minus infinity is where we get common denominators, so we can go from there. The trig functions that involve 0 or infinity, well, that's sine or cosecant, cosine and secant, and then tangent, all right? And then the two types of improper integrals are those with infinite limits or any discontinuities, all right? And that's where we'll have to create those those improper integrals with limits. So the last two things are just going over some homework problems from day 90. If you feel like you're good, no need to continue on. Otherwise, I'm going to walk through those two problems on the next page. Okay, so this is from day 90. This is number 50. So we have the limit as x approaches 0 from the right of e to the x plus x raised to the 2 over x. So if I do direct substitution right away, we have a case where it's 1 to the infinity power. So this is where we let y equal that limit, and then we take the ln of both sides, okay? So as we go through, all right, first set it equal to y. Now we're going to take the ln of both sides. At the same time, I moved that power out front. When we do direct substitution at this point, when we plug 0 in, 2 over 0 is infinity, and ln of 1 is 0. So it's infinity times 0. So in this case now, we have to do the reciprocal, right? We have to reciprocate. So what I did was I took what's going to be easiest. So I left this in my numerator, and I took the reciprocal and threw that in the denominator. Now I'm just cleaning this portion up. So what we can do is really multiply by 2 over 2. And when we do this, we end up with the limit of 2 ln e to the x plus x over x. So now what scenario do we have? Well, we have 0 over 0, so that's telling us L'Hopital. So when we L-hop it, or lop it, we're going to take the derivative of the numerator, all right? Don't forget that chain rule, and then the derivative of the denominator is just 1. Cleaning things up, right? We are just left with the limit as x approaches 0 from the right of 2 e to the x plus 1, or 2 times that quantity, over e to the x plus x, and now we can substitute 0. And so what we get is this limit actually equals 4. And so we have ln of y equals 4, and now getting y by itself, we get y to be e to the 4th power, and then if you throw that onto your calculator, we'll get that guy right there, okay? So after we make a move with our limits, we always do our direct substitution to see what scenario we're in, okay? If we're in an indeterminate form, then we have to take that next approach, all right? The last one I wanted to go through was homework problem number 62. This is where if we use direct substitution right away, we get 10 over 0, which is infinity, minus 3 over 0, which is also infinity. So that tells us we need common denominators. So multiplying this guy by x over x is where we can combine, and we have the limit as x approaches 0 from the right of 10x minus 3 over x squared. Now when we use direct substitution, we get negative 3 over 0, and negative 3 over 0 just tells us we're at negative infinity there. All right, if you have other questions from the homework, certainly we will address those, but I figured this might help solve some of those problems.